So today is the last lecture on the theoretical portion of the fundamentals. So after this lecture, next week, we are actually going to get back to more practical stuff. We're going to be looking at airfoils. But we will be looking at airfoils from the context of vortices. Basically, we'll start really building what the flow looks like around an airfoil by actually placing vortices, right, in the flow field. And that's why this week's lecture is really important in actually getting into the more practical stuff. So I know there is a homework due last night, but anybody who worked out both the rotational and the irrotational flow field on this? I know at least one person who worked out during office hour on Monday. All right, okay. So if you don't have time to do it, I'll work it out for you. So it turns out there are infinitely many possibilities for rotational flow fields. All right, as you can imagine, as I give you a hint, right? So first of all, if you look at a radial coordinate, like a polar coordinate, there is no radial velocity, right? Because all the flow directions are perpendicular to the radial direction. So Vr is equal to 0. Also, v theta, or the magnitude of velocity, is only a function of r, right? Because if you look at a stream tube that is squeezed in between two rings, the width of the stream tube doesn't change. So A doesn't change. That means rho times U doesn't change. And in an incompressible flow, that means U doesn't change, right? So basically, U can be an arbitrary function of R as long as U lies only in the circumferential direction and doesn't change with theta. Okay, I've seen several answers for rotational flow fields during lecture. One answer for rotational flow field is the magnitude of the velocity is just equal to 1. All right, I think I don't remember who worked that out. It's essentially you have Ux, right? Ux, if you look at the flow field in that direction, Ux has to be negative when y is positive and positive when y is negative. So basically that means Ux is equal to y divided by square root of x squared plus y squared, and the Uy is going to be positive x divided by square root of x squared plus y squared, right? So this is basically r. Okay, if you look at the magnitude, U would be equal to 1. So that's a good solution for rotational flow. Why is it rotational? Because the velocity, if you just look closely at a location where the streamwise velocity is horizontal, what is du dy? So if you focus on this point, right, and if you look at a flow field that looks like this, remember the magnitude of the velocity is equal to 1. So what is du over dy? When x is equal to 0, right? Yeah, 0, right? If x is equal to 0, then the square root of x squared plus y squared is equal to y, right? So y over y, Ux is equal to 1. So velocity is equal to 1. So as you move in the y direction, the velocity in the x direction doesn't change. Du dy is equal to 0. But how about dv dy? As you move, du dy is equal to 0. How about dv dx? As you move in the streamwise direction, move in the x direction, does v change? Yes, right? Oh, let me write it. I think I messed up with the notation. So So what I really want to write is this is u, this is the vector of u, this is v. Okay, so basically u and v is the velocity in the x and y direction. So dv dy, dv dx is going to be positive over here. Okay, du dy is going to be du dy is going to be 0, dv dx is non-zero. So vorticity is not going to be equal to 0 in this case. Another scenario I see people worked out is the magnitude of the velocity is equal to r, right? Which is equal to x squared plus y squared. And that means, so this is number 1, this is number 2. That means u is equal to y minus y actually over x squared plus, u is actually just equal to minus y and v is just equal to plus x. Okay, in this case, it is even easier to find out that the flow is rotational because du dy is equal to minus 1, dv dx is equal to 1. So what is vorticity? Vorticity is equal to 2, right? It's just 1 minus 1. So pointing towards out of the board, vorticity is equal to 2. All right, both are rotational flow fields. How about irrotational flow fields? It turns out there is only one possibility of u as a function of r that makes the flow irrotational. So irrotational, there is only one possible solution. The magnitude of the velocity is equal to, doesn't have to be equal to, but is proportional to one over r. Okay, if you want to derive this, you have to actually end up by deriving a differential equation, and the differential equation gets you that solution. All right, so what does that mean? That means u would be equal to minus y, not divided by the square root of x squared plus y squared, but just divided by x squared plus y squared, right? By r squared. And v would be equal to x divided by the same thing. I would recommend you to just go through the calculus and show that it is actually I can do it right now. But before I actually do calculus to prove this is irrotational, just to think about again this point, right? For this particular flow field, again, what is dv dx? As you move in the x direction, how does v change? Positive or negative? dv dx. How do you actually figure out dv dx? Right, v is the velocity in the y direction, right? So question is, at this point, what is v? 0, right? Okay, good. As you move towards the left, towards the negative x direction, what is v? Positive or negative? Negative, it points downward. As you move towards the plus x direction, what is v? Positive or negative? Positive, right? So what is dv dx? Positive, right? dv dx would be positive in this case. Now what is du dy? How do you figure out du dy, right? As you move towards the positive y direction, move up, is velocity in the x direction higher or lower? Higher, right? Because look at this. The velocity is higher at smaller radius. So as you move upward towards the center, the velocity increases. So du dx is positive, dv dy is also positive. So there is a hope of these two things cancel out, right? So maybe let's actually just do it over here, du over dy, right? Okay, again, this is a lot more calculus. So basically, you need to take derivative of the numerator and the denominator, right? So when you're taking derivative of the numerator, what you're doing is you're taking partial y over partial y, which is equal to 1. You have x squared plus y squared, right? Then you have plus, because you are taking derivative of the denominator, so the sign reverses, and then you have y over the same thing, x squared plus y squared, but squared, then the derivative of x squared plus y squared over y, right? So this is just the calculus, right? Okay, and then what we get is because dy over dy, of course, is equal to 1, and then, of course, the derivative of x squared plus y squared with respect to y is equal to 2y. So we get 2y squared over x squared plus y squared squared, right? And just to combine these two terms, we basically take the first term and multiply both the numerator and denominator by x squared plus y squared. So we get the common denominator, and we get x squared plus y squared up here, which cancels with one of the y squared, and we get x squared, y squared minus x squared, right? Okay. Same thing with dv dx, and if you do go through the same thing, there is basically a nice symmetry, right, between x and y and v and u. So what you get is exactly the same formula, but switch x and y. Okay, and you can see that sorry, and there is a minus sign. So basically there is a minus sign on top of that, right? So basically, if you look at the formula for v, it's exactly the same as formula for u, except for two things. One is to switch x and y, and two is to put a minus sign. So when you take the derivative, you do the same thing, right? You switch x and y, which you get these, and you put a minus sign to get these. Okay, that means du dy is exactly equal to dv dx, and your omega would be equal to exactly 0. All right, so this solution is probably the most important solution to the incompressible flow equation, right? You're going to see for a while. So this is really what defines a very idealized version of a vortex. So just to think about what it means. There is zero vorticity everywhere, except for, of course, at the origin, where the velocity is actually infinite, and you cannot really take the derivative anymore because it's a singularity, right? At that singularity, what we imagine is that there is an extremely concentrated vorticity that's infinitely strong but infinitely small. Of course, this is an idealization. In reality, there is usually a finite small region over which viscosity actually acts to prevent the vorticity from being concentrated exactly at a point, right? But if the Reynolds number is high enough, you can imagine that the vorticity is so concentrated in such a small region that for everything other than inside the vortex, you can imagine the flow is like in this particular case. Okay, any questions on this really singular vortex solution? All right, this really basically is a case where we have a flow field that satisfies conservation of mass and zero vorticity, right? Now a follow-up question is, what do you think the pressure field looks like? Right, I don't want you to derive it mathematically, but just can somebody give me a qualitative description of what you think the pressure looks like in this flow solution, and why? Yes, please.
More pressure in the center, and as you go out, less pressure.
More pressure in the center, and as you go out, less pressure. All right, that's a very good guess. Any other guesses? Yeah.
I feel like it's going to be the opposite because the velocity is highest in the center.
You feel it's going to be the opposite because the velocity is higher in the center,
Yes.
right? Okay, any other guesses? If no, let's vote. We have red team and what?
I kind of want to vote for his answer.
Oh.
Okay, so you change sides. Okay, so now we seems to have consensus that the pressure is lower in the middle and higher around it, right? So your argument is the velocity is higher, so the pressure has to be lower, right? That's an argument by Bernoulli. And the last lecture we did say, although we didn't prove anything, that we did state that Bernoulli is actually true, not just along streamlines, but also across different streamlines, if the flow is irrotational, right? Okay, so that is a good argument, but a different argument, I want to emphasize a different argument, because that different viewpoint is true even for these flow fields. So even for these rotational flow fields, which you said is also true, which is the pressure has to be lower in the middle and higher around it. Why? This has to do with you guys starting to learn how to read a flow field.
It has to do with the curves. It's like whenever the air curves, you draw like an arrow in the direction of curvature.
Exactly. It has to do with streamline curvature. So in general, there are two ways to read the pressure field from a velocity field, right? These are both very useful for steady state flow fields that doesn't change in time. One way is to read according to the width of a stream tube. Basically, if the width of the stream tube changes, right? If you have a streamline contraction in a subsonic flow field, you know the flow is accelerating, therefore pressure has to be dropping along the streamlines. That's using Bernoulli, right? No matter if the flow is rotational or irrotational, that works. Right? If the flow is accelerating, the pressure has to be dropping. The second doesn't depend on Bernoulli, actually, therefore applies both for in the first case, because we're using Bernoulli along the streamline, it doesn't depend on if the flow is rotational or irrotational, right? The second argument also doesn't depend on if the flow is rotational or irrotational. That's based on streamline curvature. So if the flow curves, that means something is providing centripetal force. And that something, right, in higher Reynolds number flows has to come from the pressure gradient. So the pressure has to be higher outside of the turn than inside of the turn, right? So no matter which case 1, 2, 3, which case it is, the pressure has to be lower in the middle and higher outside. It's just for the irrotational flow field, that sharp increase of the pressure, or the sharp decrease of the pressure as you get to the center is especially prominent, because the velocity increases as you go right into the middle. So what is the amount of centripetal force you need? It's proportional to what? It's proportional to u squared over r, right? And u squared is proportional to 1 over r squared. So u squared over r is proportional to what? R to the power of what? -3, right? So basically that means the pressure gradient increases very, very sharply as you go into the center. Okay, and then if you integrate 1 over r to the 3, what do you get? Right, I mean 1 over r to the 3 is the pressure gradient, right? You have to integrate that to get the pressure. What is the integral of 1 over r cubed? 1 over r squared, right? I mean, of course there is a constant. So basically the pressure would be like a function, be proportional to minus of 1 over r squared as you get towards the center. So that's what's really happening in an irrotational flow field for a concentrated vortex. And that is the reason why, like in a high moisture situation, you actually visualize, you can see the vortices, because the pressure in the center of these vortices is actually quite low, right? The pressure dropped a lot, and the pressure drops, you get temperature drop, you get condensation of moisture that makes it visible. All right. So this is the vorticity. Let me see again, like why is vorticity useful? Last time we did say that Bernoulli is actually true across streamlines, but we didn't say what. Okay, so today let's actually show why Bernoulli is actually true even across different streamlines. And here we are going to use exactly the same physical principle we just stated. That's the streamline curvature. Okay, so imagine I have a flow that's curving. All right, so it doesn't matter if the streamlines are expanding or contracting or whatever, right? And the curvature can be positive or negative or zero, right? So basically, just to consider very general flow field, but incompressible. So rho is constant. Now, let me put my coordinate system onto this flow field so that my x-axis aligns with the flow direction at the origin. All right. So previously, we have shown that Bernoulli was correct, right? In the homework, we have shown Bernoulli is correct, not just for incompressible flow, but even for compressible flows. I mean, except for the definition of stagnation pressure, it has to be more complicated, right? We have shown that along the streamline, so we don't have to do it again in the streamwise direction. But now, let's write down the momentum equation. So momentum equation in the y direction. What is the momentum equation in the y direction? So just let's write out the x direction momentum equation. The x direction momentum equation in a steady state flow and incompressible flow is u times du dx plus v times du dy plus 1 over rho of dp dx is equal to 0, right? So that's basically ignoring viscous forces. The right-hand side would be viscous forces, gravitational forces, whatever that we all ignore in this case. And what is the momentum equation in the y direction? Somebody can tell me what is the corresponding term of this in the y direction? Yeah. I switched the du over dx to dv over dx. So if you think about how we derive the momentum equation, right, through conservation of volume, conservation of momentum in a volume, in a very tiny volume. So this term actually represents the difference in the momentum flux between this phase and this phase. This term represents the difference in the momentum flux between the bottom phase and the top phase. This is the pressure force acting on the volume, right? So now if you think about the y momentum, right? Again, the first term would be the difference in momentum flux, but now y momentum flux between this phase and this phase, that actually has to do with u times partial v partial x. The u would come from the the mass flux, and the v is where the y momentum is. Then plus v times partial v partial y, then plus 1 over rho of partial p partial y equal to 0. Okay, that's the y direction momentum equation, conservation of momentum equation. All right. Okay, so in this particular case, the nice trick I did of aligning the coordinates with the streamwise direction makes v equal to 0 at that point. Although dv dy doesn't have to be 0, right? But the v actually is 0 in this case. So that term goes away. So v is equal to 0 as I align the streamline, as I align the coordinates. So u times dv dx plus 1 over rho of dp dy is equal to 0. So, okay, so now we are trying to derive the Bernoullis across different streamlines. So we're trying to see the derivative of stagnation pressure in the y direction has to equal to 0, right? That's what we need to derive in order to show that Bernoulli is true across different streamlines. So we have to somehow get rid of this ddx, and we also want to get rid of this v, right? Because, I mean, we want to show that p plus half of rho u squared is the same across different streamlines. And the, yes?
You said v equals 0 at the origin.
Yes. V is equal to 0 at the origin because we align the coordinates with the streamline. And vorticity comes into play, right? So if vorticity is exactly equal to 0, then dv dx is equal to what? Yes, du dy. Okay, then this equation becomes very conveniently u times du dx. Well, let me just multiply rho on here. So this is rho, not p. Sorry, this is rho, not p. And just to remind me if I didn't pay attention to the difference between rho and p's. Yeah, rho times u times du dx would be plus partial p partial y would be equal to 0, and that just means sorry, is it partial? This is y. Sorry, partial u partial y. Yeah, dv dx is equal to du dy. So I should change dv dx into du dy. That just means d dy of this half of rho u squared plus p is equal to 0, right? Once you have a u squared, right, you take derivative, you have to take derivative to one u and another u, add them together, the half goes away. Agreed? Okay. So what does it mean physically? What it means is that if you look at a flow like this, we are trying to see, okay, how the stagnation pressure changes in the y direction across the streamlines. So if the streams are actually like what I'm drawing, the streams are curving upwards, what does it mean in terms of the pressure gradient? Yeah, pressure would increase this way, right? The pressure would be higher below and lower above. Okay, which would drive a streamline curvature upwards. And if the streamline curvature is upwards and there is no vorticity, just imagine this case, right? It's like the flow field over here. And if I have an absence of vorticity, whenever I have a streamline that curves upwards, my velocity upwards is going to be higher than the velocity downwards. It's like this is closer to the vortex than below, right? Upwards is closer to the vortex and therefore has a higher velocity. Okay, so basically, whenever you have your lower pressure, would have to have a higher velocity. That just goes into the Bernoulli's equation, P plus half of rho u squared. Right? Whenever you have a lower P, you have to have a higher U. Okay, so that becomes one of the very useful things about vorticity free flow, right? You have Bernoulli's equation holding, right? Whenever you know, like, there is no vorticity nearby. Another very important aspect of a flow without vorticity is that, well, you can define this thing called potential. That's where the word potential flow comes from. So let me tell you why we can define this thing called potential. For those who remember multivariate calculus, do you remember this operator called curl? Okay, so if you think about what vorticity is, it's actually the curl of velocity, right? That the definition of curl is actually what so basically the definition is actually partial v partial x minus partial u partial y. So that's the definition of curl in 2 dimensions. In 3 dimensions, we'll talk about it later. It's actually a little bit more complicated, but like in the same spirit. Okay, so now do you remember if I integrate the curl of a vector over a surface? Okay, so if I draw a surface and call this S, this integral of curl over surface reduces to an integral over the boundary of the surface. Right? Have you studied this? Right? Okay. This is actually integral over the boundary of the surface u dot with dl. dl is really dl is like this small vector that basically goes along this boundary of the surface. It's called the Green's theorem. Okay, so basically that means if there is no vorticity inside of this area, then this contour integral would be equal to 0. And in particular, if I split this contour into 2 portions, into a red portion and a green portion, okay, and I somehow reverse the dl in the red portion, that means if I have 2 points, I have a point A, I have a point B, then the integral, let me see, the integral from B to A, the green portion, u dl, is going to be equal to the integral along the red portion, also from B to A, u dot with dl. Agreed? So basically, this integration from B to A is the negative, is the opposite of the integral from A to B, right, along the red line. So the total integral along this contour would be integrating from B to A along the green line, then plus from A to B along the red line, right? And that is equal to 0. That just means if you reverse the red integral from B to A, then the integral along the green and along the red has to be equal. Agreed? Okay, so that is actually what allows us to define this thing called velocity potential. A velocity potential is basically a velocity potential of this point A is defined, let me see, is defined in this way. Basically, you choose an arbitrary point in the flow field, just call it B. And that anchor, right, allows you to define the velocity potential of any other point. And that potential is just the integral from the point B that is fixed in the whole domain to that point A of this contour integral. And because it doesn't matter, right? No matter if you draw a contour here or draw a contour here, or even you draw a contour like that way, it doesn't matter, right? No matter what you do, when I draw the red arrow, what I mean is I want to reverse I did it wrong. So what I mean by trying to draw the red arrow is I want to reverse the contour. So basically the red arrow goes into the opposite direction as the contour direction of the green line. So basically when the green goes counterclockwise, the red goes clockwise, right? But then both the red and green, they point from B to A, and they get you the same integral. So in the same spirit, if you draw another line from B to A, like whatever, it encloses a different region, and as long as that different region also has no vorticity, the contour integral would get you exactly the same potential, right? That makes the definition of the potential unique if the entire field has no vorticity. All right. So basically, once you define that potential, another fundamental theorem of multivariate calculus is that my velocity field is just going to be equal to the gradient of that potential. So this is almost like the fundamental theorem of calculus, but in the vector scenario, right? So basically, if you define a scalar by contour integral of a vector, and then you take gradient of that scalar, you get back to that vector field. All right. So when there is no vorticity, there is a unique potential, and the velocity is equal to the gradient of that potential. All right. And that is very nice because it reduces having to analyze a vector field. Like whenever you're looking at a flow field, it's a vector field, right? And it's much harder to visualize and analyze and think about a vector field than thinking about a scalar field. Right? So if you know the flow field is vorticity free, is irrotational, can just imagine a scalar field. So let's go back to our previous cases and think about what that scalar field is like over here. Okay, again, we know that for irrotational flow field, the velocity is equal to a uniform streamwise x-directional flow. And what is the potential like? If you draw any, if you just pick an anchor, so let's say this is my anchor point B, okay? And you can draw any contour towards a point A. That allows you to define the potential at A by integrating the velocity field, actually backwards, integrating the velocity field from A to B, right? So what do you get when you integrate a small vector that points from A to B continuously, dot with the velocity field? Yes, you just get a difference in the x position. So basically my phi in this case, any point A is going to be equal to, well, I will just write phi as is basically equal to negative x. Right? As you move along the x direction, you get less and less potential. And the velocity, oh, I think I missed the negative sign. So the velocity is usually defined as a negative of the. There is a negative sign because in the fundamental theorem of calculus, you are going to be flipping A and B, right? So essentially, upstream has high potential. That's usually how we think about a potential, right? The flow goes from high potential place to low potential place, just like a river, right? Like a river, upstream has higher gravitational potential and flows downstream. So that's why we put the negative sign just for intuitive reasons, like grad of phi is equal to minus u. All right. How about in this case, we have this irrotational flow field, right, where velocity magnitude is proportional to 1 over r. What is the potential like in this case? And it's a little bit more convenient to think about in this case as u is equal to negative grad phi. What is phi like in this case? So on the right hand side, it's kind of convenient to draw the isosurfaces or isolines or contours of potential as straight vertical lines, right? So these are the contours of potential, and we know the gradient of any scalar field is orthogonal to its contours. The magnitude of the gradient is inversely proportional to the gap between adjacent contours, right? So if you have contours, I mean, if you just look at a map, and if you see the contours squeezed together, you know you are up for a very steep climb or descent, right? If you see contours very widely spread, it's flat. Same over here. If you see the contours of the potential field being very squeezed together, you know the gradient is very large and you have high velocity. If you see contours spread apart, then you know you have low velocity. Here, think about what the contours of potential is like. So first of all, its contours has to be orthogonal to the flow direction, right? So the contours are like that. And the spacing between the contours are exactly smaller near the vortex and bigger far away, right? The space between them is proportional to r. That means the velocity is proportional to 1 over r. Except for this case, the potential is a little bit funny because it's actually not a unique function, right? You have to actually draw a division line between here and say, okay, the potential is discontinuous along that line, and it basically, if the flow goes in this direction, it goes up and up and up and up and up over here. You can allow it to go even further up, but then the function becomes multiple values. So usually just draw a cut over here and say, okay, it jumps back to a lower value and goes up. Why is that the case? Because if you do draw a contour that encloses this vortex, then the vorticity inside this contour is not equal to 0 anymore, right? So basically, this doesn't work anymore if these two contours actually encloses a vortex. So the potential is only uniquely defined in this case if the contours, if you're integrating from B to A with two lines that doesn't enclose this central vortex. All right, does that make sense? Okay, I mean, it did took me at least a while to grasp that subtlety, but like it doesn't matter that much, like in practical purposes. All right. Any questions regarding to the velocity potential? Okay, basically for vortex, the velocity potential has I can write phi is equal to theta, right? Theta being the angle. So that's yeah, that's how we usually define it. Okay. So let me see. Yeah, so this is the two cases. Okay, this also brings up another concept, that is circulation. So circulation is really just gamma is really what we usually call it. Is basically equal to the integral over a surface of that vorticity. Okay. Of course, you can also write it as integral over like a, well, let me just the usual way to write it is partial S, which means the boundary of S, U dot with dl. Okay, so that's basically using Green's theorem. And circulation basically is how much vorticity you have in a closed contour. And it's convenient because you can compute circulation using two ways. One is basically just integrate how much vorticity there is inside this closed contour. And two is you can trace along the boundary of the contour and see how the velocity is aligned with the boundary, right? I mean, that also gives you the circulation. And in this particular case, right, you can see that if I draw a contour if I draw a contour like that, okay, one is I know the vorticity inside it is 0, so the circulation should be 0. And two is that when I integrate along the contours, I know these two radial sections gives me 0 integral because the velocity is perpendicular to the dl. And on this outer part, I have a longer dl but smaller v. On this part, I have a higher v and a smaller dl, and the direction is, and therefore the sign is opposite over here and over here. So I get a 0 circulation. On the other hand, if I integrate over here, right, I get non-zero circulation because the dl is either aligned or opposite to velocity, right? So I constantly integrating something that is either positive or negative. Okay, and another consequence of this is that no matter what closed contour I draw, right, I can draw a closed contour that is like that, and getting back like that, right? I know the circulation is going to be exactly the same as the red because the gap between the red and the black contain no vorticity. All right, so that's how circulation is going to be also quite useful. Okay, we want to touch a little bit on how vorticity move. So we know that when there is no vorticity, the flow stays with no vorticity. But if there is areas where the vorticity is concentrated, we know vortices, right? We need to know how the vortices are going to move in the flow field. So to understand that, we are actually going to use exactly the same equations we tried to derive in the last lecture. So basically, at the end of the derivation, we basically said that partial vorticity, partial t, is equal to 0 when there is no vorticity, right? But when there is vorticity, we can still derive a similar equation, but that equation becomes partial omega partial t plus omega times the divergence of velocity plus velocity dot with the gradient of vorticity is equal to 0. So that becomes the equation. If you just recall what we derived the last time, right? So this term actually turns out to be the vorticity times the divergence of velocity. And this term turns out to be velocity times the gradient of vorticity. So these are the two terms that comes out of the same derivation. Okay, so from this equation, what we can see is that assuming incompressible flow, then this term is going to be 0, right? What you get is just the partial derivative with respect to time plus the derivative along the velocity direction. The sum of these two components is what we call a material derivative or Lagrangian derivative. So this is the material derivative, sometimes also called the Lagrangian derivative. It basically is the derivative with respect to time if you follow a small particle that goes along with the velocity u in the flow field. Okay, so what that means is that vorticity is just like a small particle in the flow field, right? So if you have a vorticity of 0 and you go along at a certain point and you move along with the flow, the vorticity of that new point as you trace along the flow field is still going to stay 0, right? If you are at a location where the vorticity is non-zero, let's say positive value, then you go along with the flow field, right? And at the new location, the vorticity is still going to be that positive value. In other words, vortices just go along with the flow field, go along with the flow. I mean that's why if you look at again, like we will watch movies of vortices a little bit later. If you look at how the vortices meander and move, that's basically how the flow is moving in the surrounding area. And a similar conclusion can be derived for circulation, right? Because if you draw a closed contour, that closed contour is going to move to a different place as the flow is evolving, right? So let's say it has deformed by surrounding vortices, right? I mean, the flow field around it, the flow field doesn't have to be uniform, right? So the contour can be deformed. But still, within the same contour, because of this, right? The entire contour would have exactly the same integral of vorticity. Oh, that is actually even true for compressible flow, where the divergence is not 0. You're going to see that when the divergence is positive, right? If this is positive, the flow is expanding, and it actually makes this go negative, right? I mean, this is a positive one. If you move to the right hand side, it'll be negative, right? It'll basically dilute vorticity. That actually, but again, the area of this contour is going to increase to compensate. So basically, everything cancels out. No matter what the flow is doing, expand or shrink or deform or whatever, the total vorticity within this closed contour is not going to change. So the circulation dt is also going to be equal to 0. And that property, that law, is actually extremely useful, especially when we go to 3 dimensions. We're not going to use that. We're not going to do things in 3 dimensions a lot in Oh, I should say, we're not going to be doing complex things in 3 dimensions a lot in 1600, but like if you go to more advanced courses, this is going to become more and more useful as you see like a complex 3-dimensional scenarios where there are vortices being transported and stretched and turned and whatever. And you know that if you follow a closed contour in the flow, the total vorticity or the line, the contour integral of velocity doesn't change. That's immensely useful. Okay, so that's basically how vorticity and the circulation would move, is that they just go along the flow. So finally, we want to really understand. Now we understand how the vortices are moving, right? How does air flow around vortices? Right, so we know that if you have no vorticity, you get no vorticity at the end, right? If you do have vorticity, for example, from air flowing around a wing or something, right, you know there might be vorticity coming out of the solid body because the viscous interactions on the body is actually not negligible, right? And then we also know how vortices move in the flow. They just move with the flow. Finally, if we understand how the air around vortices would move, then we pretty much understand the whole flow field. Okay, so in the beginning, I mean, in the end of last lecture and beginning of this lecture, we already have seen how air would flow around a single vortex. What is it? Yeah, it goes around, and basically u is equal to, in this case, the u velocity is negative at the positive y, so no, it's x. But in this case, we are saying, okay, the vortex has a circulation of gamma. Okay, how does that modify this equation? If I just have this flow field, what is the circulation? Any idea in how to find out? Try to integrate it, right? And the easiest way to integrate it is to integrate over, because I know it doesn't matter what contour I draw, right? So I'm just going to draw whatever contour that is most convenient. And what's more convenient than a unit circle? So if I draw a unit circle, right, what is the velocity along that unit circle? If the velocity field is over here, what is the magnitude of velocity? Yeah, 1 over r. And if I have a unit circle, it's just the 1, right? Now, what is the length of the contour? It's 2 pi, right? So the total circulation for that flow field is going to be 2 pi, okay? Okay, now if I have a circulation of gamma instead of 2 pi, how would that help me modify the flow field? Just multiply everything with gamma over 2 pi, right? Okay, if gamma is 2 pi, then that modifier is 1, right? That multiplier is 1. If gamma is twice as large as 2 pi, then I just multiply the flow field by a factor of 2, and I get the integral being 4 pi, right? So, yeah, so that's how the air would flow around a single vortex that is stationary in the flow field. What if the vortex is actually moving itself? Well, we know the vortex cannot just move by itself without the flow moving, right? The vortex has to go with the flow. So if the vortex is moving at a velocity of, let's say, u0 in the x direction and v0 in the y direction, then the whole flow field needs to add a u0 and v0 in the x and y direction respectively. Then what we have is this flow rotating while moving along a single direction. And the vortex just moves with it. right? Any questions on what the flow field is like around a single vortex? Yes?
At what point is there a point in the diagram that it's U0 or V0? Like,
Can you say again?
like added U0 and V0, is there like what point in that like getting like U0 and V0?
Oh, so U0 and V0 is the velocity of that
Oh, just like
vortex.
oh, okay.
Right, so basically this is a general flow field, right? And you have three parameters. One is gamma, the circulation. Two is U0, the x velocity of that vortex, and the three is V0, the y velocity of that vortex. So basically you have a valid flow field no matter how you choose these three numbers. Okay, so now a critical insight we get is, how about you get a pair of vortices? What would the flow field be like if you have two vortices of equal but opposite circulation? Anybody could think about like what approach we would use to figure out what the flow field is like around the two vortices?
Just add the two different velocities. Which one?
Just add the two different velocities with each other. That's an excellent answer, right? So a nice thing about, well, a really nice thing about incompressible flow is that a valid flow field, a valid velocity field, right, can be obtained by adding two valid velocity fields, because the only constraint a valid flow field has, it has to be divergence free, right? Basically, incompressible flow conservation of mass ensures that there is no partial rho, partial t. And the only other term in the conservation of mass equation is proportional to the divergence of rho u, right? And if rho is constant, that means divergence of u is constant. So if you have one flow field that has divergence of u equal to 0, you have another flow field whose divergence of u is equal to 0. In this case, the flow field around that vortex only, plus another flow field around this vortex only. You add them together, you get a valid flow field. And by the way, this is exactly, not exactly, but almost exactly what a flow field behind an airplane is going to be like, right? These would be the tip vortex coming from the starboard wing. This is going to be the tip vortex coming from the port side wing, right? And you have the flow in between them going down, right? That's what's providing your lift, right? Through conservation of momentum. That flow field is also what drains your energy through induced drag, right? Because this flow field contains kinetic energy, right? Basically, the flow field can be written as, so let's say this is origin, and this is x, and this is y, right? The velocity field, considering only the left vortex, would be u equal to, in this case, as y goes positive, I have positive u velocity. So y divided by y squared plus not x squared, but x, let's say the distance between the vortex and the origin is b, and there is another b over here. Then instead of x squared, I would have x plus b squared, right? And my v would be minus x plus b over y squared plus x plus b squared. Now for this vortex, I would have u equal to the opposite direction, minus y. Again, I need to multiply both by gamma over 2 pi. So let me just multiply this over here. Gamma over 2 pi, gamma over 2 pi. Okay, and for the what we call induced velocity from the right vortex, from the other vortex, it's basically the contribution to the flow field from that vortex is called the velocity induced by that vortex. Y squared plus now x minus b squared, right? Because when x is equal to b and y is equal to 0, you have, at the center of that vortex, you have infinite velocity. And v is equal to, in this case, I get plus, so x minus b y squared plus x minus b squared. Again, times gamma over 2 pi, gamma over 2 pi, right? So basically, if you add them together, that will be the flow field. All right. Oh yeah. One side note is that if I am considering, if you look at this flow field, right? One question I want to ask you to figure out by yourself, I'm not going to tell you, is that what is going to be the velocity of these two vortices for an actual airplane, right? In which case I know that the flow field very, very far away from the vortices has 0 velocity. If I know the velocity far away has 0 velocity, then what is going to be the speed of these vortices? Try to use the principle of what we just learned, right? The vortices just go with the flow. So that has consequences, right? I mean, as an airplane passes by, would the tip vortices be moving up or moving down? Do they become wider and wider? Do they become narrower? Like, what do they do? They become wider. Why is that?
So that they notice it, right when the plane's gone through, they have some kinetic energy. Then kind of, as the plane goes infinitely far away, like that air goes back to being still, such that they have to get wider.
That's an interesting argument. So yeah. So the air becomes stationary again. Actually, not through viscous effects. Right? I mean, it becomes stationary again because although viscous effects are small, they eventually, if you give it infinite time, I mean, it'll slow the air. So basically, it does slow down, but not through the mechanism we are talking about here, which is assumes the flow being inviscid. Yeah, we have seen like in the single vortex case, right? You can add a uniform velocity to the flow field and the flow field is still valid, right? In this case, if the flow field is actually the flow field behind an airplane, other than adding these two vortices together, should I also add a uniform velocity? Yes? What uniform velocity would I add? The velocity of the airplane. Yeah. So I think it depends on the frame of reference, right? If I choose a frame of reference that stays with a free stream, not with the airplane, right? Then mean, the airplane actually travels in the out-of-board direction, right? So we are looking at the two-dimensional flow field where we're ignoring the velocity in the out-of-board direction.
The velocity of the airplane pushes the air down.
The velocity of the airplane pushing the air down. Well, in this solution, right, even without adding a uniform velocity, we can actually see that, just imagine you are in between these two vortices. So x would be greater than minus b and less than plus b. Okay? What is the v velocity? What is the vertical velocity? So if x is greater than minus b, x plus b would be positive, right? So the contribution from the green vortex would be negative. The contribution from the red vortex, because x is less than b, the v would also be negative. So automatically the flow in between these two vortices would already be moving downward without even adding any uniform velocity. Actually, the uniform velocity you should add depend on what the flow is doing when very, very far away from these vortices. Imagine if x and y, or any of either x or y, is very, very large. What is the contribution from the green vortex? Velocity be proportional to what? 1 over r, right? So it's going to be 0. What is the contribution from the red vortex? Again, it's going to be 0. So if you're adding a uniform velocity onto the flow field, that means even very, very far away, you have some velocity, which is actually not true, right? For the wake behind an airplane. If we choose the frame of reference that stays with the free stream air, stays with the ground. So no, you are not supposed to add any uniform velocity, right? The flow field just comes from the sum of these two vortex contributions. Okay, now imagine what is going to be the velocity of these two vortices. Okay, just to give you a hint, the way to think about it is, imagine you are at the center of this vortex, right? When you are zooming in, the vortex no longer is a concentrated point. It starts to become a finite region. And as you imagine, you go into the right of the center of the vortex, so that the contribution of this vortex itself to the velocity at the point you're looking at is going to be 0, right? Because the vorticity around you are all in all directions. The vorticity above you tries to move you towards me. So okay, so if you have vorticity above you, right, in this direction, it tries to move you towards the right. But vorticity below you is trying to move you to the opposite direction, right? So if you have vorticity all around you in a symmetrical way, the contribution of this vortex itself to your velocity is going to be 0. So the velocity comes from just that vortex. And that velocity is towards which direction?
Down.
Down, right? So essentially the way to think about how a vortex moves is to think about what is the effect of everything other than that vortex itself. And we know that the vorticity moves with the flow field, right? So figuring out the velocity of the flow field is figuring out the velocity of that vortex. So in this case, we know both vortices would be moving downward because they are going to be moved down by the other vortex. So the velocity of the vortices is going to be, right, if we plug in, for example, if we plug in B onto this V, what we get is 2B divided by y squared plus, not y squared, y is equal to 0, x minus b. So basically also 2b squared over here, gamma over 2 pi, right? That would be equal to gamma over 2 pi times 1 over 2b. So that is how fast the vortices itself is going to be moving. All right, so that means as the airplane passes by, the vortices would start to sink down slowly. Okay, any questions on this? So let's actually briefly touch very quickly how vortices is moving in 3 dimensions. So vortices in 3 dimensions are basically the same as vorticity in 2 dimensions, except for you have to consider, let's imagine this is the 2D plane. What we have done before, vorticity in 2D would be the component of vorticity out of the board, right? To figure out the component of vorticity in this direction, you have to imagine I have a board in this direction, right? I do the same analysis. Figuring out the vorticity in that direction, I have to imagine I have a board that lies horizontally. I do the same analysis. So basically, omega is going to be having 3 components. The first component being dv dx minus du dy. Oh, not the first component. That's actually the z component. Sorry. This is going to be the last component. Okay, and the first component, you actually get the dv dz. 1 second. No. So basically, I'm trying to do it a circular way. So v is here. So when I have dw dy minus dv dz in the first component. The second component would have du dz minus dw, which is the velocity in the third direction, dx. Okay, so basically the 3 components are exactly the same way, but just imagine I have different boards aligned in different directions. Okay, and this, of course, is the curl defined in 3 dimensions of velocity. And one of the nice things about analyzing vorticity in 3D is that, again, it's a vector calculus thing. The divergence of a curl is always equal to what? 0, right? So that means there is no divergence in vorticity. And when there is no divergence in vorticity, there is no volume integral. So if you integrate the divergence of vorticity in any 3-dimensional volume, it is equal to 0. And you remember there is this Gauss's theorem that the volume integral of divergence is equal to the surface integral, right? I mean, we did this in the conservation of mass momentum and stuff. The surface integral of the dot product with the surface normal. So this is a famous quote called "There is no end in vorticity." There is no end. Why? Because if you have a vortex that ends some point, right, and you draw a volume around that endpoint, then vorticity would go in and doesn't come out. And this would not be 0, right? So that proves there is no end in vorticity. But now is the end of the vorticity lecture. So I will see you next week. There is a recitation on Friday, but starting from next week, we'll go back to more practical stuff, use what we learned in Vorticity to start working on two-dimensional airfoils. All right.